Yeah.
Yeah,
We have a legal responsibility to keep you safe, but we have no responsibility to keep ourselves safe. That's just the way it is.
Yeah, but like here, if you're sitting at the desk filling out your own paperwork, and she looks at you and she's like, "No way, you're good. Like, do you need gloves on right now?" No, I'm just writing things.
And then if you're using a Bunsen burner, you shouldn't be wearing gloves because they're flammable, right?
Yeah.
So like you're risking horrific burns if you're wearing them.
She wasn't sure when people are supposed to be wearing gloves in the lab.
She's a true instrument. So like, I don't understand when you're supposed to wear gloves.
I mean, it depends what you're working with at the time. That's what dictates whether or not you put gloves on or not.
Forensics, shouldn't you want to have gloves on anyway to like not contaminate?
I mean, yeah, forensic laboratory is all the time. I'll give you that one.
Well, it doesn't matter. Sarah just interprets the results.
She's like, "Oh, this is my DNA. Just take that."
Just take it out. I just put my hands in it.
We don't do biology stuff in our courses. We don't care about that.
Yeah.
Anyway,
I mean,
bile.
if-
Moving on to bile.
Did we already talk about bile?
Did we talk about bile? I thought we got to bile.
I think we got to bile, but we didn't talk about it.
Right, consensus. Do we need to talk about bile? Yes or no?
Well, we must do because
Tell us about bile.
Yeah.
So, starting with bile, let's go back one slide just to make sure. Yeah, we did hair. I'm sure we did hair. Okay, so we're talking about the different samples that a forensic toxicologist would collect. It's part of either the, well, if we're talking about bile, autopsy at this point. Bile used to be commonplace in terms of the samples that would be collected. And the reason it used to be commonplace is that instruments were not particularly good back in the day. And bile was one of the places where illicit drugs would sort of concentrate. So it was collected because there was a high level of illicit drugs within the samples relative to other toxicological samples, which means you have a pretty good shot at detecting illicit drugs there. These days, instruments have gotten considerably better, so it's less required, I guess, that you go for bile. But still, you know, there's lots of methods out there for analysing illicit drugs and those types of things from the sample, so it's probably worth collecting. Do we know where bile comes from?
the gross places.
The gross places. We need to be a little bit more specific than that. It's not the stomach.
It's from the gallbladder.
Gallbladder is a good answer, but it's not correct. That's a storage place for bile, so that's where you would find it, but not where it's created. Liver, very good. Comes from the liver. This is why you can take your gallbladder out and you're going to be somewhat okay. It's because the liver actually creates it and it gets stored there. Point of bile is it's a surfactant. Do we know what a surfactant is?
Means it has hydrophobic and hydrophobic components.
Does that
And
mean
in your
it's-
kitchen, where would you find it?
Detergent.
Detergent, it's a dishwashing liquid. And it does exactly the same thing. It dissolves polar stuff and it dissolves non-polar stuff equally well. So it creates these structures here. If you have, so looking at it, we've got our polar groups on the outside and we've got our greasy chains in the middle. So if we look at bile, we think about illicit drugs, they're generally non-polar greasy things. The illicit drugs are going to migrate into the center of this and then they can be transported around that way. So this could be moved into, I don't know, the small intestine to shift it around places. So bile's used to allow us to absorb really, really greasy stuff. So if you eat, fish and chips, a highly greasy meal, your body's not particularly well set up to absorb all the fat that's in that meal. But the bile is sort of the way the body gets around that. You can absorb a whole bunch of fat in here, and because it's a surfactant, it allows it to be shifted into the body more easily. Illicit drugs, kind of fatty, same sort of deal. It can be used to excrete both neutral and charged species. That shouldn't be changed, that should be charged. Typically molecular weight's 500 to 600 Dalton, which is a pretty good match for illicit drugs. So, you know, the size is right. The fact that, you know, it allows non-polar species to go in is right. It says excretion, so it is a strategy for getting rid of stuff. As you said, it's created in the liver. So if you had some sort of toxin in your body that was highly grease or lipid soluble, your body would struggle to get rid of that, because if we think about the excretion pathways we've talked about, we have the urine, which is water-based, not very good for getting rid of, fats and those sort of things. So we have this specialized system in the liver to create a liquid, I guess, a fluid that we can dissolve the really greasy things into to shift it out of the body. So it's good for absorbing fats and it's good for excreting fats as well. Yes, you can excrete drugs such as opioids, cannabinoids, and benzodiazepines using bile. So that's one of the reasons why the toxicologist wants it. It's an excretion pathway for those types of drugs. It gets dumped into the intestines, so it's not going out through the urine, it's going out the other way. Yeah, you can detect illicit drugs by this method even when it's undetectable in the blood. Moving on to gastric contents, useful detecting any recently ingested drugs. Common sense, if it hasn't found its way into the body, it might just be sitting in the stomach. So it's something that will always be collected. Just for curiosity of the toxicologist, they're always going to be looking what's in the stomach at the time. I suppose the other reason is that if you want to know about drug uptake or alcohol uptake or that sort of thing, whether or not you have a full stomach or not is going to impact the rate at which these things are taken into the body. So if you have nothing in your stomach, the uptake of drugs is going to be faster than if you've had a large meal. Yes, skip on to the next one. Liver. Liver is the first major organ to which drugs are distributed after they have been absorbed from the gastrointestinal tract following oral administration. So let's say you ingest drugs. First place it's obviously going to go is into the stomach. However, if it's going to do any actions on you, it needs to get into your circulatory system. Okay, there's not many drugs that actually impact the stomach based on you taking them in. Antacids, I guess. But all the illicit drugs that we're really concerned with, they're generally going to be impacting your brain. To get there from the stomach, it has to get into the circulatory system, into the blood, to travel around, to get up to here, to do things up in this part. Now, first stop in the journey, once you ingest a drug, it gets into the stomach, it gets into the blood supply, all of that blood supply is funneled into the liver. Why?
Take out any poisons.
Exactly, to protect your body. Evolution has realized that we're not very smart. If we encounter a new plant or something, we're like, I wonder if we can eat that. If we do eat that and it happens to be the wrong plant, we're going to ingest a whole bunch of toxins. Based on that, anything that you eat is going to be funneled directly into your liver first for screening. All drugs, they will wind up at the liver first. Thereby, it's the first organ where you get a concentration effect of the drugs. If it's something where you get a horrific overdose pretty quickly, you may discover that you have a very large amount of drugs in the liver based on, it just congregates there before moving elsewhere. So many drugs and their metabolites are found in greater concentrations in the liver than in the blood for that reason. Good news about the liver, it's often still available after putrefaction has ruined most of the other samples. So, your blood's gone, your urine's disappeared. Basically, you putrefy sort of, outwards going in. Your liver's quite well protected. So that means it's one of the last organs to really start to break down and degrade. It's got a funny shape like this, and if you take samples from the liver, they may have different concentrations in drugs depending on where you sample it. The reason for that is the blood flow into the liver is sort of funneled in different ways. So over on this lobe, I think that's connected directly sort of to the stomach. So you can get absorption into the blood around the stomach, and then that goes into this part of the liver. Whereas if it goes further down into the small intestines, that gets funneled over to the bigger side over here. So if you're going to sample this part of the liver and this part of the liver, you might find different concentrations of drug, basically because it's been absorbed and entered the liver from different points in the drug's journey. It says best to look in the left lobe. That's the bigger one. That's probably because all of that comes from the small intestine. So you get most of your absorption from the small intestine, which means you're probably going to get more representative results there. Summing up, be familiar with all these toxicological samples that I've talked about. It's kind of annoying that I've talked about it between 2 separate weeks, but you can thread those together. We're nearly done with last week's content. A few of the other types of sample that are less common but you may encounter as a toxicologist are insects. So this is when we get to sort of extreme levels of putrefaction in terms of a body. We know about insects and time of death and that sort of stuff. It's entomology. Is that covered in your degree anywhere? No, not really?
Briefly.
I think first year.
You get a guest lecture on it maybe?
Yeah.
Yeah, no one's an entomologist that I know in the forensics program, so I don't see any of us teaching it, but you may have had someone like Matt from the police come in who's an entomologist. But anyway, first step in the journey if you take drugs and then you die is the drugs go into you. You then die. Drugs are in your flesh, pretty much with nowhere to go. Those drugs could break down. So, your liver is still just a big sack of catalysts that break stuff down. So stuff in there may be broken down. But if you have like an amount of drugs sort of diffused in your muscle or something, they're pretty much just going to sit there. That flesh will decompose and insects are probably going to colonize you and start eating that flesh. So because you have sort of an overall concentration of drugs within you that the insects are going to consume, they are going to build up a concentration of those drugs as well. Maggots eat the flesh, drugs are in the maggots. Here is a list of the studies where they've looked at the different types of drug, I guess, that was in the flesh that was consumed by the insects, and then they detected the drugs inside the insects. So there's a whole range of different types of drugs. Amphetamine, I think these are sort of, barbiturates down here. What was I going to say on this? It may not necessarily just be the drugs that you're detecting because you've got obviously metabolism in your body, which is the breaking down of drugs into their, other species, more water solubilizing ones to kick them out. But insects themselves have their own metabolism, so you could find metabolites based on insect metabolism as well. Next slide is a grisly picture of a dead person. There's just one. It's black and white. Should be okay. But so here we see colonization of, do we know why or where insects colonize primarily?
Where is it like there's a lot of fluid?
Yep. Moist areas is a good answer.
Right in the eyes.
Yeah, pretty much. Why? Yes, pretty much, it's wherever there is an opening into the body. That's where they're going to go. So, if you think about just like your arm, it's a pretty solid barrier. There's no real breaks in it. Whereas if we think about, your mouth, eyes, all these stuff, there's ways for the insects to get in there, get at the nutrients. Wounds, those sort of things, they're also sites where insects will congregate and colonize outwards because it's sort of a break in your outer skin protection from them.
At least their teeth look good.
Yeah, no, it was
Like
like
that.
that.
They look kind of happy. They're like, yeah.
Happy, really?
Good smile.
Okay, so when we get to putrefaction, we're getting to fairly terrible toxicological samples to work with. So we're thinking about, black goo that's probably been scooped up out of the body. There is a regime that you would apply to that sample, and it's pretty much acidification, basification with organic extraction. So you guys have done, organic extractions from aqueous solutions. Think about that. You're generally going for organic components because that's what illicit drugs effectively are. So we start with our fluid or deprotonated sample. So probably that means we're running it through a centrifuge, getting rid of the solids, working with the liquids. You're going to just take the organic phase because any of your samples are going to be water-based. Organic phase, you're then going to do an extraction with alkaline. So that's going to remove alkaline. That's going to deprotonate any stuff. Think of carboxylic acids. It's probably the classic one. So you're going to get deprotonation of those. They will stay in the base and you'll get the organic fraction of that. Then you're going to acidify it and do another organic extraction, and that's going to give you the acids. You can go on the other side, and then we do, so what's the first step? Acidify. You get the aqueous sample, so that's going to be any of your amines that get protonated that step. They're going to go over here, neutralize, extract the organic, and then you acidify, and then you basify, and you're collecting the organic fractions as you go through it. You might be asking why you're acidifying and then basifying, and then acidifying and then basifying. The reason you're probably doing that is you're doing different strengths of acid and base as you go. So you're sort of separating by pKa or pH. So you get your really weak acids first, then you get your stronger acids. It's just a way of, matrix effect. You're trying to limit the amount of compounds that you're doing. So if you do multiple washes with stronger or weaker basic solutions, you're going to get different compounds out as you increase the strength of the extractions you're doing. Oh yeah, it would be horrific. The classic, you'd have the stuff under your nose when you'd be working. Right, so just to give you an idea of some of the pKa's, what's a pKa?
The log of the...
Or what's a basic, whenever we're talking about a pKa, what are we generally talking about? pH, and what's a pH?
It's the measure of protons.
Yeah, pretty much. So it's basically whether or not you can deprotonate or protonate something. Okay, that's the pKa. It's sort of the general pH whereby you get an equilibrium between protonation and deprotonation.
Oh yeah, I remember that.
Yeah, right?
It's been a while, but yeah.
Yeah, it's relevant to toxicology because if we look, we have all of these different interesting, not even illicit, like, pharmacological compounds here, and they all have varying degrees of pKa. So what that means is if you change the pH and you do an extraction, sometimes you're going to extract some over, but others are not going to be extracted over. So you can play around with the pH of the solution, do your extractions, and you'll start specifically extracting maybe, let's choose one with a horrible name, chlorpromazine versus, say, cocaine, because they have very different pKa's. So you can hone in on one based on the pH that you're doing. It's really tedious, but it works. So, it's on a slide. Right, I've talked about post-mortem redistribution a couple of times. We may as well go over it one more time, sort of a hint that you might get a question on it when it comes exam time. Post-mortem redistribution is when drugs or chemicals move from one site to another in the body after death. So typically this is going to be from a place of high concentration. It's just going to diffuse on its journey to a place of low concentration until you get to equilibrium. So we've talked a little bit about drug reservoirs. So this would be if you take a whole bunch of drugs in condoms and they're in your stomach and one breaks, you've instantly got a great reservoir of drug in your stomach. Very high concentration. It's probably going to kill you, but over time, your dead body, it'll start to diffuse outwards into the organs that are nearby. So initially, stomach has extremely high concentration of heroin. Liver's right next door, so that means slowly over time, a couple of days, the concentration will go up in the liver. Same with...
I was gonna say, it's like when people try and smuggle drugs on planes, just like pops it.
Yep. Instant OD, but then again, wow, good news for them. Good news for the toxicologist is generally they would make it to a morgue really quickly. So post-mortem redistribution is not going to be such of an issue then. It's more if someone, dies in the woods, you find them 5 days later, they're still going to be mostly intact if gross, but you're going to get, a lot of post-mortem redistribution based on that. So the rate at which post-mortem redistribution occurs, it depends on the relative concentration gradient. So back to the stomach full of heroin, that's a very high concentration. So that is going to relatively quickly diffuse outwards because you've got high concentration, low concentration next door. It's like a glass of water and you add cordial to it. Initially, you're going to have dense cordial in one place, but then it's going to very quickly expand outwards. Time, obviously, the acidic or basic character of the drugs or the metabolites. And that comes down to if it's going to go from one place to another, it's going to have to cross a membrane. Okay, it's the same rules apply. So if you're going to cross a membrane, you ideally need your illicit compound to be neutral in state. If it is, it can fairly quickly cross the barrier. If it's highly charged, it's probably going to be sort of contained for a decent amount of time. There is post-mortem circulation where blood does pump within a body after you're dead. Does require another person though. It's kind of a special case. We generally don't talk about it very much, but be aware if someone has, suffered an overdose, someone's going to try to save them, right? And that does involve pumping their heart, even though they're dead, if they can't be resuscitated. You kind of have to include that in your calculation time, I guess. So main chemical reservoirs are the stomach, the liver, and the lungs. When would the lungs be a reservoir?
When you smoke it.
Yeah, when's the most likely time that you would encounter a large amount of smoke and you die? Fire, arson, same. So in that situation, you're going to be in a very smoky environment, you're going to be dead, and you're probably going to get some migration from your lungs into the surrounding tissue. And the heart is next door to the lungs. So that's why if you are analysing the sample from someone who has died in a fire scene and you only take blood from the heart, you may discover there's a high cyanide level into it because they've breathed in a whole bunch of cyanide. There was cyanide in the lungs. We've got post-mortem redistribution, so the cyanide has migrated slowly into the heart blood, and it might trick you into believing that they died by cyanide poisoning. Whereas in reality, if you took blood from multiple different places, you'd say, oh, actually the level is quite low in the other regions. It's probably just this post-mortem redistribution effect that has amplified the signal in the heart blood. Yep, I just talked about heart blood. We don't want erroneous interpretations. Those are bad. Yeah, this is why we collect blood from multiple sources. The main other place, which I've also mentioned, is from the femoral artery. Actually, no, that's wrong. From the femoral vein. Why don't we collect from the femoral artery? Nope.
Is the artery the
Oh, close.
the oxygen?
So where's it directly come from?
It comes from the heart.
Exactly. So we don't, if our heart blood is contaminated, say from a fire scene, and we collect from an artery, it's literally just come from the heart. So there's a high chance it will also be contaminated. If we go for a vein, that's been on a journey around the body and it's going back towards the heart. So we have the best chance of not seeing that contamination from a vein rather than from an artery. So yes, it's deep, but we are not above digging down to find those veins. This comes back to no blind sticking. So if you're going to take blood from the femoral vein, you need to be able to see the vein to do it. So this involves cutting down, finding the vein, and then injecting directly from there.
It's like how big the vein is. It's huge.
It's pretty big. It's got a whole leg to feed.
Did not expect it to be that big. Not gonna lie, maybe I'm crazy.
So if you got a cut there, a deep cut, you're pretty much screwed.
Yeah. I mean, the artery would be worse,
Yeah.
but the vein would not be particularly better.
Is arteries the ones that like spray?
Yeah.
Arteries.
Artery's high pressure, veins lower pressure because it's sort of flowing back.
Yeah.
Yeah, I think this says elevate slightly, but it doesn't mean squeeze. We're not allowed to like squeeze for blood because that creates, stuff will flow into the blood from the surrounding tissues and potentially contaminate your sample. That's it. We've gotten through last week's lectures. We're only 25 minutes late, but that's all right.